Okay, I don't know if anybody saw that first video, but I'm gonna have to delete it. Ooh, maybe I should delete it now. No, I'll delete it later. Just leave it there for somebody to trip up over. So the homework is to do first number 4. And you know what? I'm not even going to do number 4. I'll just show you the work for number 4. Because that's just so straightforward. That's just a straightforward application of Newton's universal law of gravitation, or law of universal gravitation. This, I don't like the way I wrote that. I'm going to write it again up here. Big G times, basically there are two different masses. So sometimes I like to use a big capital pointy M for one mass and a little m for the other. You could call it M1, M2. Here I kind of tried to do both, but I messed up. So I'll draw the picture here, but I'm not going to do the calculations. I'll just show you the calculations. So here's the 100 kilogram mass, and here, or a student, and these are students, 60 kilogram student, and the distance between them, between their centers of mass, is 1.7 meters. So that's the R. This is one of the masses. This is the other mass. And calculating the gravitational force between them, which would be this force and this force, equal and opposite because of Newton's third law, kind of like tension, is done this way. So this is big G, the gravitational constant, and this is the mass of one student times the mass of the other divided by the square. Don't forget to square this. And the units for the constant are chosen so that these 2 kilograms get canceled out. This m squared gets canceled out, and we're left with newtons. And it's a really small force. Alright, that's where I messed up last time. Number 8 is the next one you're supposed to do, and the orbital radius of this orbiting object is 30,000 kilometers. So I used the radius of the Earth just a minute ago, and that'd be a fast satellite, but it would run into things. So we need the velocity of a space station orbiting the Earth with this orbital radius. And for this, there's a formula you can use, but I'm not going to give it to you. You're going to have to either memorize it or derive it every time. And deriving it's no problem. That's what we did here in number 11. And I'll just do that again, just so you can see. If you ever get messed up, here's what you do. So we've got the Earth, which I'll give it a big M. And then we've got this thing out here, this space station or whatever it is. That's the little m. Although those m's can be switched around, doesn't matter. And this is just a plain old Newton's laws problem. I'm going to write net force 2 different ways and then solve for stuff. So the net force, anytime you've got something in a stable circular orbit, meaning constant speed in a circle, is the mass of the thing. This thing's going to be my little m times v squared over r. That's the net force, because the acceleration is v squared over r. And the net force is also the sum of all the forces acting on the object. So the net force on this object, there's just one force acting on it, and it is the centripetal force. It is the net force, and the kind of force is gravity. So gravity is pulling this straight in. It's also pulling this straight out, but we're just focusing on this object right now. So these two expressions of net force only apply to the orbiting body, not the thing that's being orbited. So there's only one force acting on this. There's no drag. There's no, I guess you could call this weight, but we've got a new name because I'm going to use a different formula for it. So net force is the force of gravity. So this equals that, except when I write this equals that, I'm going to substitute in the formula for the force of gravity. The force of gravity equals that, so I can say mv squared over r equals big G, gravitational constant, times the mass of one of the objects, that'd be the Earth in this case, times the mass of the orbiting body over r squared. I've got the object mass on both sides, so I'll divide both sides by that. That goes away. And then I've got some r's on both sides. I'm going to multiply both sides by r, multiply this by r, no r's left, multiply this by r, I just got one r in the denominator. So I have v squared equals big G, big M over r, and if I want v, it's just going to be take the square root of both sides. I get big G, big M over r. Let me make that consistent. Alright, so that's the one I want to use in this situation down here. And so I'm going to need the mass of the Earth, which I've got, was given in that question, and I'm going to need the orbital radius and G, and they're all given. G is right here, and the orbital radius is right there. But the tricky thing about this orbital radius is it's in kilometers. So right now we've got 3 times 10 to the 4 kilometers, and each kilometer is 1,000 meters. So I'm going to be multiplying that by 10 to the third, so it's going to be 3 times 10 to the 7th meters equals r. Alright, but basically this formula. So the velocity is the square root of big G, which is 6.67 times 10 to the negative 11th newtons, kilograms squared over meters squared. That's that. And then times the mass of the Earth, which is 5.972 times 10 to the 24th. Kilograms. Divided by r, which in this case is 3 times 10 to the 7th. Alright, I know some of you are really into your calculators, so you'll have a preferred way to do this. Some of you just have sort of ordinary mortal calculators, and this is how I do it. Everybody has their own ways, but we're going to get into some really big numbers and really little numbers, and you've got to be careful with these exponents. So what I do is I'll multiply. I'll just forget about the scientific notation for a second. I'll do that in the end. So instead of this times this times this times that divided by this, I'm going to do all the numbers that are not scientific notation first, and then I'll incorporate the scientific notation. 6.67, because that's the way I like to do it, times 5.72 divided by 3 equals. Alright, so I've got that, but that's multiplied by 10 to the negative 11th times 10 to the 24th. If I multiply those together, I just add the exponents. 24 plus negative 11 is 13. And then to divide by 10 to the 7th, I subtract 7 more from the exponent. So 13 minus 7 is 6. So this is 13.2 times 10 to the 6th. I am going to use this function on the calculator now. And then I need to, so I've got everything in the radical. I'm going to take the square root, 3,643, or 44. I'll just round it to, yeah, whatever, 44 meters per second. Check my answers from last year, make sure I got it right. Yeah, that's good. I actually rounded then. Let me round now. What's next? The next one, number 10. So hopefully I had you change this from 3 RPM to 4 meters per second. Otherwise, this is a tricky kind of a problem. And I don't know if I'm going to do the work. Maybe I'll just show you what I did. Maybe I'll rewrite it. So on this one, cover this up here. I'll show you what I did. Drew my picture, and I might add a little bit to this picture just to make this a little bit more organized. So got a 50 kilogram adult. There's the adult standing on a bathroom scale on a Ferris wheel, and it's rotating at 4 meters per second. The scale reads 600 newtons, so that's the normal force. We've been over this before. If you're standing on the ground, the force of the ground pushing you up, that's the normal force, which is the scale reading. So based on the scale reading, we know the normal force. What is the wheel's radius if the scale reads this when the person's at the bottom? So there's more I can fill in. I know the mass of the person, so I can multiply that mass times 9.8 to get the weight. So in my picture, I've got all the forces acting on the person. There's just the normal force pushing up, the weight pushing down. You can see they're different. There's going to be a net force that's upward. One thing and I've drawn in that there's acceleration upward. So one thing I could also add is, if I wanted to, net force is upward. And I could write the value of that net force, but I've done it over here. So net force equals mv squared over r. And this is like, remember how in all those problems we used to say net force equals ma, and net force equals the sum of the forces, and then we would set this equal to that and solve. Well, now net force is not ma anymore. Net force is mv squared over r for circular motion. And the sum of the forces, the sum of the individual forces acting on the person, we've got a normal force which is positive because it's up, and the weight which is negative because it's down. So here's where I've done this. This is like the old ma, except it's circular. And this is the sum of the individual forces. So here's my big equation. I just need to plug stuff in and solve for whatever's left. So mv squared over r becomes 50 times 4 squared over r. And normal force minus weight becomes 600 minus 490, which is 110. So to solve this, you would just multiply both sides by r, and then divide both sides by 110. So the answer ends up being 50 times 4 times 4 divided by 110, which is 7.27. All right, let me see on this next one if I want to do it from scratch. Calculate the acceleration. Yeah, this one I'm going to maybe do a little bit from scratch. So the acceleration due to gravity on the surface of the sun, given the sun's mass. This is another one where there's a formula you could memorize, or you could just derive it every time. And we derived it back here, or we will have derived it back here, maybe here. Formula for g in terms of the Earth's radius and mass. Let's see if that sounds like it would work. We're looking for g. This is basically g for the sun, given the mass and the radius. Yeah, so that's the formula that we need. And I'll derive it again over here. So weight is the force of gravity. I'm just going to write weight equals mg equals the force of gravity. So that's what weight is. And we've got a new way of expressing the force of gravity. We can call it big G times the mass of one mass that's accounting for this gravitational pull times the other mass. You've got to have two masses to have gravity. I have some mass, the Earth has mass, so together we have a gravitational attraction. You can't just have gravitational, well, I'm not going down that rabbit hole. So this is weight, this is also weight, so these two things are equal. So I'm just going to write them like this. mg equals big M, little m over r squared. So this represents, let's just say this is my mass, and this is my mass, and this is the Earth's mass. So if I want to find my weight, I multiply my mass times g, 9.8. And another way of finding my weight is to multiply my mass times the Earth's mass over r squared, and left something out, big G. So there's a little m on both sides. We can cancel those out and we get a formula for G. G is big G times m over r squared, and that's how we found 9.8 down here when we used that. So I'm just going to use the same formula again. G equals big G times the mass of the sun over r squared. So this would be the mass of the thing whose acceleration of gravity you're trying to find. So this is 6.67 times 10 to the negative 11th newtons kilograms squared per meter squared times oh, the sun's mass. I was thinking that doesn't look like the mass before, but before we did the Earth's mass. 1.99 times 10 to the 30th kilogram over the radius of the sun, 6.96 times 10 to the 8th meter. Got to make sure that this is in kilograms and these are in meters, and if they're not, convert. But in this case, we're okay. Right, so here's the way I do it. 6.67 times 1.99 divided by 6.96. And I get that. That's going to be easy. So now I can just do the 10 to the whatever. So 10 to the negative 11th times 10 to the 30th. I just add these. 30 minus 11 is 19. And then dividing by 10 to the 8th means I subtract another 8. So 19 minus 8 is 11. So this should be 1.91 times 10 to the 11th. And the units are going to be meters per second squared. Let's see if that's what I got when I did this before. No, that's not what I got. Shame on me. Do you see what I did? I bet some of you do. This is supposed to be squared. Dang. Alright, so here goes again. Don't do what I did. Well, you probably did. You're following me right off the cliff. So 6.67 times 1.99 divided by 6.96 squared equals. So I've got that. And now I'm going to do 30 minus 11 is 19. And then I'm going to divide that by 10 to the 8th squared, which is 10 to the 16th. So 19 minus 16 is 3. So 0.274 times 10 to the 3rd is the same as 2.74 times 10 to the 2nd. Or I could just do times 10 to the 3rd, which is going to be 274. So 274 meters per second squared. And that's the right answer. Or at least that's the answer I got last time I did this. And one last one, number 13. Where is number 13? Satellite orbits the Earth at in a stable orbit at a constant speed of 7,800 meters per second. What's its distance from the center of the Earth? So this sounds a lot like a situation where I can use this formula again. Let's see. V equals the square root of big G times the mass of the thing. So this is whatever's being orbited. This is the orbital radius. This is velocity. So constant speed, that's the velocity. G, I know. The mass of the Earth, I can find from an earlier question. So yeah, it's just plugging these things in and solving for R. And instead of doing all those steps right now, let me just show you my work from an earlier time. So I wrote this down a little bit differently here. Instead of V equals this, I have V squared equals GM over R, which is true. It's just squaring both sides of that. It's just in the derivation of this, kind of going back a step. So V squared is 7,800 meters per second squared, and G is 6.67 times 10 to the negative 11th. And then the mass of the Earth is 5.97. You can find that from earlier in the handout. And then I just kind of have R equals there. So to arrive at R, let me show you how I would do the calculation on this. Maybe that's useful. I skipped a little step here. So multiply both sides by R. So R is over here. And then divide both sides by 7,800. So 7,800 squared is down there. So this looks a lot like what I just did. 6.67 times 5.97 divided by 7,800 squared equals. And then I'll deal with the exponents. 24 minus 11 is 13. So it's going to be times 10 to the 13th. So I get that, which looks like 6.5 times 10 to the 6th. Yeah, 6.55 times 10 to the 6 meters.